Welcome to my channel. Today we look at more other applications of dot product, and we'll be looking at how to apply dot product in real life situations. Previously, we had looked at other applications of the dot product. For instance, we saw how the dot product can be used to tell if vectors are orthogonal, parallel, or neither. So today we'll be looking at how to use the dot product to calculate work done. Now, when force is constant, force that is applied on an object, if it's constant, then work will be defined by force times the distance. That means that you're applying force on an object, and then that object moves through a given distance. And then we can get work by multiplying those two, force times the distance. There are some cases where that is, you see, in this case, force and the object should be in the same direction, should be moving. Force should be applied in the direction of the object. The direction the object is moving. So there are cases where force is applied in a different direction, a different direction that is different from the motion of the object. So in that case, we do not calculate work as force times distance, but how we calculate work is that we would multiply the component of the force that acts in the direction of the motion by the magnitude of the displacement. So we're multiplying this component of force acting in the direction of the motion of the object multiplied by the magnitude of the displacement. So that's what we'll be doing. We'll be looking at those two scenarios. One where force is applied in the direction of motion of the object, and the other scenario where force is applied in the opposite direction. So in cases where force is applied in the opposite direction, then how do we get work done? So that is the question. How do we calculate work done? And so, supposing this is our force, which we can write in terms of the x component, y component, and the z component, and r is the vector along which force is applied, then work will be defined as the dot product of force and r. And we know how dot product is defined, that in the dot product will be the distance or the magnitude of force times the magnitude of r cos theta, where theta is the angle between force and the line of motion. So supposing this is the line of motion, supposing this is our line of motion r, and supposing that this is force, and then this is the angle between force and the line of motion. So this is our theta. This is our theta. So we're saying, therefore, to get work done here, we'll take the magnitude of force times the magnitude of r times cos theta. That's what we're doing, and I've drawn a diagram just for this illustration. So that figure 3 is here. This is our figure 3. So supposing this is our force and this is r. So this would be the angle between force and the line of motion. So this would give us theta. Now let's look at examples on how to calculate work done. The first example here, the question is find the work done if an object is moved along this vector and force that is applied is given by this. So force that is applied is given by 7I minus 5j minus k. So find work done. So work done will be given by force dot r. Force dot r. So this is our force, 7I minus 5j minus k dot 2I plus 3j minus 7k. And we know how to get the dot product, that this is given by 7 times 2, which should be given by, that is 14. And then negative 5 times 3 would be negative 15. And then negative 1 times negative 7, which would be 7. And so this is 21 minus 15, which is 6 units. Which is 6 units. So this is work done. And we, of course, we know how to manipulate this. We did this before, how to get dot product. We did that before. So if you missed that, you can check in our earlier video on how to get the dot product. Let's look at another example of how to calculate work done. And the example is calculate the work done when a force of 60 newtons is applied at 45 degrees to the ground to push a box for 30 meters. Give your answer to 4 decimal places. So in this question, we've been given force in newtons, and we've also been given distance moved when this force is applied. So to get work done, it will be force dot D. Now, so the magnitude of, so this one is a dot product, and we know it is defined by the magnitude of force times the magnitude of D cos theta. Of course, theta has been given to us as 45 degrees. And so the magnitude of force is 60 and our distance is 30. So 60 newtons times 30 cos 45. On your calculator, doing this, you get 1272.7922 Newton meters. And Newton meters, you can write it as joules. You can write it as joules. So this is approximately this. I just rounded off to the nearest whole number. So we've used this for the dot product here. And this is the formula for the dot product. Let's look at another example, slightly different from the first two. And the question is, and in this question, force has been given as a vector, just like in the first example. A force of 2I minus 4j plus 5k is used to push a sleigh from point P to point Q. Calculate the work done if force is measured in newtons and the distance is measured in meters. So here we've been given the points from which the box is being pushed. Now it's a sleigh. Is being pushed from this point to this point. So these two would give us a displacement vector. So the displacement vector from P to Q will be given by the point Q minus point P. So 6 minus 2 gives us 4, and then 4 minus 1 gives us 3, 9 minus that gives us 6. Which we can write as 4I plus 3j plus 6k. And we apply a formula for getting work done. And the formula is that work done is given by F dot this displacement vector. And F has been given to us as 2I minus 4J plus 5K dot, and the displacement vector that we've obtained is this. So doing that, let's just do it and see what we get. 2 times 4 is gives us 8. Negative 4 times 3, that gives negative 12. And 5 times 6, which gives us 30. So this will give us, at this point of negative 4 plus 30, which gives us 26 Newton meters or 26 joules. And that is the work done. And so that is how we calculate work done if we are given force and distance. And that is a very good application of the dot product.